Sorry for being late a little bit. My name is Andrey. I work in Uber in New York. I'm an SRE, which means I'm as far away as possible from our clients and as close as possible to the hardware and the computers that we use. So usually I try to structure my talks in such a way that there is a problem, and I try to explain why the problem is a problem. Then there is a part about what kind of solution we can have for this problem. And I'm trying to explain why this solution is actually a good one. So to start with the problem, it's not a simple one for this talk. It's a little bit complicated, and it has many sort of different angles that you can look at it. So one of the angles is that it's not fast enough. So we use, in Uber, we use a lot of different technologies and different frameworks and different other things. So my team, for example, I work in the observability team, which is basically everything related to metrics, monitoring, alerts, that kind of stuff. So we run a Go service, actually many microservices, but in the long run, it's like one super service written in Go, and we have a lot of load. So we ingest a lot of data, millions of data points per second, a lot of data getting queried, and last time we estimated our query, we have 75 years of data queried per second. And that means that we have to really think about how this whole thing works, because we can't just throw new machines into the pool. It will never work. It can't sustain itself. So after some looking into this, after some analysis and after some investigation, we found out that our code is not doing what it's supposed to do. I mean, yeah, of course, it does all this ingestion, it does all this querying, but a huge chunk of its runtime is spent in things like garbage collection, context switching, stalling for memory access, contending on different parts of like code of mutexes and everything like that. So we figured that it's probably a good idea to look into this a little bit further, because we can probably save money, save time, and make our users a little bit happy. So to kind of keep it a little bit more interesting, I'll start with benchmarks and then explain everything else. So I had to strip it a little bit from sort of NDA stuff, but the basic idea is that we did some things with our code without actually changing the code, and it helped us save, in some cases, up to half of the runtime, basically making things run faster by 2x. And this trick doesn't really, it's not really specific only for Golang. It can work for general case, and that's why I have Nginx in front of it, which started to run a little bit faster as well after the magic. So this talk is going to be about this magic. So to explain why the magic actually happens, let's talk a little bit about computers. So some years ago, maybe 10 years ago, computers were really simple, and everybody could understand what's going on inside them, right? So the computer was a very simple device. I mean, it's not, of course, that simple as it might sound, but still, it was a simple architecture, right? You have a CPU, you have a memory, you have some bus interconnecting them, you have maybe some peripheral controller hub, you have disk attached to that. It's very easy. And when you run your program on this kind of computer, you can understand and reason about what's going on, right? You could understand that, okay, so this is the CPU, so if my code is running, that means the CPU is executing it right now. If I need to read some value from the memory, well, this is the memory, this is the speed of the memory, this is the throughput, this is the bandwidth of my bus, so I can calculate actually what's going on. It's no longer the case, unfortunately, and the modern servers that we use and everybody else is using they are very complicated devices with multiple cores, multiple cache hierarchies, with different special parts of CPU that try to predict what's going on in your code and try to optimize towards it, and sometimes it works, sometimes it doesn't. So what it ends up to be is that when you run the same code on the same CPU, on the same server, but at a different time, it can have a completely different latency, it can have a completely different behavior, and it's really hard to know what's going on. And hardware manufacturers, they provide us with tools that can help with this, like, for example, PMUs or PABS. But so far, like, if I go through the internet, the only person I see that actually is using them is Brendan Gregg from Netflix. And he's really trying to push towards that, but I don't really see that this effort kind of takes space and people actually start to use all these tools that the hardware manufacturer provide us. There was some change in the kind of landscape of this with the rise of eBPF, which is a recent cool new thing to profile things and to instrument your code on Linux systems. But still, it's pretty much young and shiny and nobody really using it, unfortunately. So yeah, this guy said that Crookes-Moore's law doesn't really work anymore. So let's look at this at least cryptic diagram. Not really good at drawing things, but I tried as much as I can. So what do you think this is? A what? Jobless factor? Chocolate factory. Okay. Well, maybe. Where's the chocolate? Any other versions? Nope? Okay. So to me, it looks like a network, right? We have servers. They are connected to each other in the network. We have some sort of attached storage with these cylindrical things, right? And then we have some sort of a router, the blue box there, and internet, which is the cloud. And maybe we have some cold storage, like a tape device or something like that attached there too. So, I mean, this can be like a rack in the network, for example. Or this can be the whole network if the company is not that big. Or it can be a virtualized environment in Amazon, for example, right? So if I put labels onto it, then yeah, that's what it might be, right? You can have SSDs, you have serial attached SCSI somewhere, and that kind of stuff. But I can replace labels without changing the picture, and it will start to look like a single server, right? We have cores of a CPU, maybe multiple CPUs, and we have some sort of very fast interconnect between them, which can be the network. I mean, you can imagine that it's a network. You have your fast storage attached to it, which is your memory, and then you have a PCH, which is a peripheral hub, and you have your cold or slow storage attached to it, which is your SATA disk or maybe some SSD or something else and whatnot. And then you have your network controller, which connects you to the outside world, which is, in this case, not the internet, but some other computer in the same network. So what I need a drink. So what I'm trying to show with this picture is that the modern computer is not really that far away from being a network on a chip anymore. Years ago, it was probably unexpected, and people couldn't really imagine that this could happen, but this is what we have right now. We have these complicated systems on a chip that are actually resembling a network, and I think that we should actually start thinking about our servers as networks on a chip. So talking a little bit more about computers and the performance, let's talk a little bit about devices that we use, which are our disks, which are our network cards and everything like that. So the trend right now is that the gap between the performance of different parts of the computer, it grows instead of contract. And what we have is that because of this gap growing, is that the latency characteristics and throughputs of different components is so different right now that we actually have to take this into account when we write our code. We don't, and a little bit later I'll talk about what happens because of that. But basically, the most obvious things that happens is that, for example, one CPU core cannot take the input from one network adapter anymore. Basically, if you have one core in your network card and you saturate your network, your core will stall. It won't be able to keep up with the speed of the network. So there are, for example, some applications out there that are forced to switch to user space polling. They just bypass the kernel and they poll the network card directly because, what was that? Because that's the only way that it can actually achieve the target throughput goal. One of these applications, like a good example, is, for example, the C-star framework. It's open source on GitHub. You can take a look at that. This is like full 100% Intel GPDK-based user space kernel bypass. And they prove there with benchmarks and everything that this thing actually runs like multiple times faster than the normal TCP stack because they bypass the whole thing. And they can control the hardware directly without going through all these levels of complexity and abstractions in the computers. So yeah, going back to this, computers grow in complexity. They stop growing in quality, as in like the performance of the actual system, and they try to just put more and more complexity in the system and add more components, thinking that this might somehow help us engineers to build better software because we now have this new special device or this new special node or something like that. But more often than you think, we just need the computers to actually compute and do nothing else. Just compute, crunch numbers, send data. That's it. We don't need anything else from you. So the solution, I put solution in quotes because it's not really a solution. So we have this problem at hand. We have these systems that grow more and more complex. We have systems that have more and more components with growing gap of performance, of latency, of throughput, and everything like that. We have systems that are not simple anymore, and the usual abstraction, like von Neumann machine that we were taught at schools, it doesn't really stay true anymore, because you just can't reason about the systems as a processing unit, storage unit, and interconnect between them. It's not like this anymore. So the problem exists. So I would have expected that the industry came up with some solution for this problem, because it's a huge problem. So the solution we have right now is that let's not think about it. Let's just pretend it's not really happening. So the way this thing is solved, or maybe worked around, or not solved right now, is that the engineers who build languages and language runtimes and systems, they sort of resort to operating system to solve the problems for them. And they expect the operating system kernel to take care of the hardware details, kind of, so that the operating system takes care of all this hardware complexity and abstractions, and then we'll just write our code as if nothing really happens, and the operating system will just solve it for us. So you won't believe what happened next. This is just 3 quotes from different documents on the internet. I'll explain what each one of them means, which show that this is not what's really happening. So the first one is, for example, from the design document for glibc malloc, which is the memory allocation function that almost virtually every program uses in Linux. So the quote basically says that malloc doesn't care about hardware. It doesn't optimize for NUMA, which is non-uniform memory access, when you have different memory banks attached to different cores with different latency characteristics between different memory banks. It doesn't care about NUMA. It doesn't care about thread locality. It doesn't sort threads by core. It doesn't do anything at all, and it expects kernel to do this for it. Another one, oh, actually, that was the second one, not the first one. No, that was the second. No, that was the first one. That's right. Okay, so the second one is the quote from the design document for Golang runtime improvement, which was, and maybe still is, I hope, meant to add hardware understanding to Golang runtime. So the quote is that right now runtime doesn't try hard to ensure any locality resources, and resources are pooled. Resources being processors, which is like Go unit of Go routine execution. Resources are memory caches. When garbage collector deallocates memory, it doesn't really give it back to the system. It actually keeps it for a little bit so that maybe we can reuse it later. So all these resources are pooled. And pooled means that there is a huge pool in the runtime and everything is in it. So we don't care about hardware locality again. We don't care about hardware topology, nothing like that. And runtime in general is not aware of system topology. And the last one is quote from the Golang GitHub. Basically, there is an issue. It's closed now, but it's closed with a workaround. So the issue was about that the GC, when your software, when your app runs hot, and you have a lot of garbage, so GC has to kick in quite often. So in this case, GC does so much memory access that the Linux kernel decides that the GC is the actual work, not the actual code that runs on the system. So it starts to migrate memory towards the core that runs the GC. And then GC stops, and your actual program starts to run, and you have to migrate memory back. But then GC kicks in, and you have to migrate memory back again. And it kills a lot of performance. So for example, this last issue on GitHub was closed with sort of like won't fix. It wasn't really fixed. And the explanation was that, so we'll just sort of hack around it a little bit, and we'll just bind memory to like a core so that we disable the kernel here. So basically, what happened there is that instead of fixing the problem, we will disable the thing that we were supposed to rely on so that now nothing is aware of hardware at all, and even this runs faster. So here's the another cryptic diagram. So here I try to depict the Go runtime. So I'm still really bad at drawing things, but let's try to figure out what's going on here. So let's start from top to bottom. The top thing, M, is that all these weird letters are actually the official names of things in Go runtime. So M is the meshing thread. So when the Go runtime tries to run your code, it spawns a number of meshing threads, like actual Linux threads. And this number, I mean, it's supposed to be equal to Go max procs, but it's not true. So usually this number is slightly larger than that. Sometimes it's a lot larger than that. So if you want to if you run Go code in your production, you want to check it out, there is a flag you can specify to the Go runtime, which is, I think, shed debug. It will tell you the debug information about the scheduler. It will print it to the standard output. And it will tell you the number of actual meshing threads running right now, number of idle ones, number of active ones, and whatnot. So basically what happens is that, yeah, the number of meshing threads that will run your Go code right now is equal to Go max procs. But there will be a number of idle threads just hanging around, just in case. And there will be a number of threads that are running syscalls right now, and the number of threads that are running cgo right now if you use cgo in your code. So you usually do some syscalls in your program. This is like the normal thing. If you read from a socket, for example, or write to a file or something like that, you use a syscall. So a number of threads will be locked in syscalls, and to maintain Go max procs sort of invariant, there will be more meshing threads than you expect. The blue thing here, the blue rectangle, is the P. P is the processor in Go terminology. So processor is sort of like a logical structure, logical thing that runs your Go code. So P has many things, but two most important things is Mcache and runqueue. So runqueue is the runqueue, obviously. That's the queue of Go routines that are scheduled to run on this P. And Mcache is the memory allocator cache. So when the GC collects memory, it will first put it into the Mcache, so that maybe we can reallocate it later if your program queries for it or something like that. And the last thing on this diagram is these two green things. The net pole is the network poller. That's the thing that actually kind of waits for the I/O, which is usually the network I/O, and wakes up your Go routines that wait for it and tries to schedule it and actually does all the input-output. And M heap here is the memory heap, which is like the actual pool of memory that we use when either Mcache is empty or the allocation request is so big that we can't serve it from the cache. So what I tried to do with this diagram is to show you that these three things are completely not related at all. The red circles, green rectangles, and blue other thing. So not related at all, when I say not related at all, I mean that there is no effort to bind these three things together or try to ensure any kind of sort of locality or synchronization between them. So what happens during the runtime of a Go program is that we have a Go routine running, so we have a Go routine we need to run. So we need to find a P for this Go routine first. So we look through all the Ps we have and find the one with the shortest run queue. Then we put our Go routine onto this run queue. But P is not by itself a thing. We need to schedule it as well on a machine thread. So then we look through all the machine threads and we find a idle one. If we have an idle one, we just assign our P to this idle machine thread and it starts to run. For example, if this machine thread, if this Go routine makes a syscall, which what usually happens in the short run, right? You do some computations and then you need to read from the network, write to the network, read from a disk, or do something like that. So when this Go routine hits a syscall, this machine thread sort of kind of, it becomes locked, and it is removed from the pool of machine threads that can run things for you, because now it does syscall. And if there was other Go routines on the run queue of this P, which is now locked with the machine thread as well, we have to remove them all from there, put them to some other run queue, and this other P will run on some other machine thread. So what happens is that you run your code, it allocates memory from one of the caches, for example, if it can happen, or from the M heap if it can't, then it runs for a while on one of the threads. Then you do a syscall to read from the network, for example. It gets descheduled, it gets moved away, and it starts to run on some other machine thread. So after the syscall is complete, right? So your code executes, you get on the syscall, you wait a little bit, then the syscall completes, you try to acquire the same machine thread first. This is the only optimization that exists in the Golang. If you fail, and you usually fail, you get assigned to a different machine thread. That means that your CPU caches, your NUMA node, all your registers, everything will probably be flushed, and nobody cares about it. So you don't even try to do a lot of locality here. If you lost your P, which can happen if, for example, you slept on a Go shed or something like that, which is like not a syscall way of descheduling your Go routine, which happens a lot too, then you will lose P, and by losing P, you will lose Mcache. So if you next time allocate memory, you will allocate memory from a different cache, which can be on a different core, which can be on a different NUMA node. So Linux will have to migrate pages for you, so that's what happened in this previous ticket that I showed. So good thing is that there is a paper which is not versioned right now, so I don't know if it will be implemented in Go 1.8 or 1.9, or if it will be implemented at all. So there is a paper that is meant to add this sort of hardware understanding to Go runtime, but it's not there yet. And what we have now in Go runtime is weird workarounds, which they're not supposed to work, they work by accident. So I call this wishful thinking in engineering, because we really, really, really wish that things are that simple and that we can just write code and it will just work for us. Well, it will. It will to some extent, but that's not the way to go, because as this paper for the Go runtime, for example, stated in the first paragraph, if you take a look at the pace of the development of computer systems, the pace with what the core number grows and memory and caches bloat and everything like that, then you can probably imagine that in a few years we'll have systems with like massive number of multiple cores. Not 4, not 16, but thousands. We already have the systems. Like PlayStation 4 runs on a processor that have like thousands of cores. There are CPUs out there that already have hundreds of cores. They're just not mainstream yet, but they will be mainstream in like a few years, for example. That also means that even the current model, where in like the NUMA model, where you have memory banks attached to cores, attached to CPUs, like physical packages, and that makes your memory architecture non-uniform, this model will actually be outlived by a model where each CPU package will have so many cores that you will have to attach multiple memory banks to each package. That means you have to think even more about what kind of memory access patterns you have. And the problem is that the trend of hardware development is this, like let's make things more complicated, because we really hope that engineers are smart and will try to make use of all this complexity to their advantage. And the trend in software engineers is like, whatever. As in, let's build more abstractions on top of our hardware, because these guys just keep adding this complexity. We can't understand that. Let's just abstract it all away. At the same time, we try to over-engineer everything we can by, like, if you take a look at any, for example, modern Node.js frameworks, this is absolutely ridiculous. And we just keep adding indirections, as in like, okay, so memory access, like NUMA access is sort of complicated right now, so instead of thinking about memory partners, we'll just add this special NUMA manager in the kernel, and it will just take care of this whole thing for us, which it doesn't actually do. Or, for example, so we have this multiple cores, so instead of actually thinking what kind of course we run and like what kind of code we run and what kind of course, we'll just sort of add the special indirection, which is the scheduler, and this thing will just figure out for us in some way without us actually telling it what to do, which is a little bit unexpected for me, at least. So virtual machines add to this kind of abstraction pie. Automatic memory management, as in like GC and transaction memory, for example, which still is not a thing in mainstream production, but I think it will be at some point. Garbage collection, abstraction of hardware, all these things, they add to this abstraction pie that basically eats away of the performance of the hardware that we use to run our software. So yeah, we basically end up running our apps in multiply nested virtual machines. We virtualize everything, including network, disk I/O, like everything possible, even memory. And we, for some reason, hope our software to better utilize the hardware, even though we try really, really hard to get as far away as possible from hardware. So, a workaround. Don't have a solution. Maybe there will be a solution. Maybe some smart people from MIT or, I don't know, Stanford or somebody else would figure out a good solution for that. I don't know, I'm just an SRE. I'm not even a software engineer. So a workaround in my book is something that will help us for now, and it can scale a little bit maybe until somebody else would figure out the rest of the problem for us. So the workaround for me is a computer-friendly engineering approach, as in like a computer-friendly engineering sort of philosophy. It goes sort of the opposite way of the current trend, which is human-friendly engineering, sort of, like software engineers-friendly engineering, as in let's make our frameworks and our languages and everything else as friendly to the end users as possible, so that it's very easy to produce code and produce value for the users, right? But this will come at the cost of removing, or actually adding more abstractions and removing this kind of bond that existed between the computer language or a framework and the actual computer hardware, right? Like in the C world, you just talk directly to your hardware, basically, if you want to, but in JavaScript, for example, you just can't do that. So before talking about the actual workaround that we came up with, I'm going to do a little sort of like a little deviation here. So very important thing that we realized at some point when we were trying to optimize our code and our apps in Uber is that intuition is like the biggest lie ever in software engineering. So Mr. Knut used to say that premature optimization is the root of all evil. Actually, I think it wasn't him. He was the guy who popularized this quote, but it wasn't his quote. So if premature optimization is the root of all evil, then intuition is like a department store. You can go and buy as many routes as you want, and it will deliver it to your home for free. Because humans are really, really, really bad at guessing, predicting, and rationalizing about computers and how they work. And I've seen many, many times when people think like, okay, this is like the bottleneck in my code. I'm going to optimize the hell out of it right now, and everything will run faster. And then it ends up this code was used like once, ever. It's actually a dead branch or something like that. So the only way, and probably not the only way, but the best way to ship the best code is to ship any code you have right now and see what happens. That's what we learned. You ship the thing you have, and then you get the feedback from your users, from your clients, from your other fellow engineers. And this feedback is your best code profiling tool, because these people will tell you like, I don't know, this form loads slow. I don't care that your computation is not that slow, but this button is not that good. I don't want to wait for it, or something like that, right? Or, I don't know, this thing runs good enough, and that was the thing you spent 1 week optimizing for. But this other thing is so bad, I can't really use your product anymore because of that. This is your best code profiling tool. There's nothing better than that. You can use any kind of Intel vTune Extreme Edition or profiler optimizer, and it won't tell you that users will complain about this part of the code. So if you have feedback loop, use your feedback loop. This is the first thing you need to use to actually do things. But if this opportunity is exhausted, then we go to actual profiling. So thankfully, this is the thing right now. This is the hotness. Everybody tries to profile their code right now. Golang is probably the best language to use if you want to use all these tools that we have right now. So the Go developing community and the Go authors, they added a ton of cool, great features and tools to Golang that can help you to optimize and figure out what's going on and to understand what is the actual way your code works. So there's just a list of like general things. So even if you don't write in Golang, you can use Linux perf, you can use eBPF, you can use systemtab. If you don't run on Linux, you run on FreeBSD, for example. You can use dtrace. These are all the tools that can help you to look into your code and to understand what's going on there. So eBPF is the thing that is being promoted right now by Brandon Gregg, including Brandon Gregg, a lot. I think the slides will be available later. So here's the link to a very good starting point to learn about eBPF and how it works. It has a lot of resources, starting with very simple things like, what is eBPF, why do I need that, and ending with things like, let's write Lua plugin for kernel. So it really helps to understand how your code works. You can instrument everything you want from your user space code to Go Runtime, for example, or whatever other runtime you use, to kernel. And you can see the whole stack of calls, and you can understand what's going on. The flame graphs is the sort of like a toolkit that was built by Brent Gregg. It helps you convert the output of all these tools into these shiny graphs that can help you understand what's going on in your program. I have two, a red one and a blue one here, to sort of make a point that there are two types of analysis you can do with your program. Two very big clusters. One of them is the hot flame graphs, which is what my program is doing right now and where it spends the most time crunching numbers or doing whatever it's doing. And the other one is the off-CPU analysis, which is what my program is, where my program is sleeping right now. It's like it's not doing anything, so something is happening, right? Why isn't it doing anything? So this kind of analysis can help you understand, like, okay, so we wait a lot for I/O from the network, or we sleep a lot on the disk operations, or something like that. So this is the analysis of what your program is doing when it's not doing anything. And that actually is very important as well, because when you look at the flame graph, it doesn't actually show you, or when you look at the output of any profiling tool, it doesn't actually show you like what amount of time this whole thing actually takes out of the time you have available, right? So you have 1 second of CPU time and you run for 200 milliseconds. The flame graph will only cover this 200 milliseconds. The other 800 milliseconds you waited for something, they won't even be there. You will never notice it unless you actually look for it. Then there is language-specific profilers. For example, Golang has a built-in pprof profiler that can actually generate these flame graphs on its own. And it also have different other kind of visualization. It actually can generate you PDFs, for example, right out of the box. Then there is a tool that we wrote at Uber. It's called GoTorch. It's on GitHub. So basically what GoTorch does is that if your program has an exposed pprof HTTP endpoint, which you can do with like 2 lines of code in Go, then you can use this tool to connect to your program remotely and it will generate you real-time flame graphs of what's going on right now, and we use it a lot. Yeah, and then there are commercial things like Intel vTune, for example, that is really good if you want to pay. We don't. So this is the last part of it. So this is about the magic that we had. So there are 3 things that you all know about that we kind of thought about again, and we tried to implement these 3 things together to form something that can help us to work around the problem that we have right now at hand. So I'm just going to cover these 3 things real quick and explain how these things work out in our environment. So sharding, everybody knows about sharding. You have sharding in all databases, basically. Like, I don't know, MongoDB can't live without sharding. MySQL usually is sharded. So if you look at the Wikipedia article for sharding, this is the quote from the Wikipedia article. Sharding is like a horizontal partition of data in a database or a search engine. And the fact is, it's not entirely true. You can shard whatever you want, and we already do this. For example, when we put a load balancer in front of our, like a pool of our servers, we shard this thing, but we don't have the data. We shard the computation. And because we don't have the data, instead of the key, we use the source address and the destination address, or some combination of these 2 as the sharding key. But this is sharding. It's not different. So keep that in mind. Load balancing. It's also a very broadly used thing. It's used, I think, virtually everywhere. So according to Wikipedia, again, load balancer is a way to distribute workloads across multiple computing resources. And the main purpose of load balancing is to maximize throughput because you have more links, minimize response time because you have more boxes that can respond to you fast enough. And you avoid overload of a single box because you can kind of redirect your load to another computer or cluster or something like that if the first one is overloaded. So normally you use load balancers as a network device in a network, and you put it in front of a number of computers, and your load just goes away to all of them. But since computers are in fact networks on a chip, why don't we put load balancer in front of CPU cores, right? That kind of makes sense. So, and you can do that. You can use Nginx or HEProxy or whatever for this, and you can actually run multiple instances of the same program on the same computer, and you can put a load balancer in front of them so that the external client will still see this thing as like a 1 instance, because it will still listen on the same port 80, for example. But you will have multiple instances of the same program running behind this local load balancer, and this will sort of kind of build on top of the idea that computers are actually networks in a box. And the last thing is the hardware locality. So this is probably the most important part about this. So again, Wikipedia quote, network topology is arrangement of various elements like links, nodes on a computer network. So hardware topology is basically the same thing, but inside a computer, right? We have CPU cores, we have memory, we have different interlinks, we have peripheral hubs, we have disk, we have everything, and this all are connected with different links. So why don't we talk about the computer locality then, like the hardware locality and hardware topology? So we use Docker for that because it has a built-in support for CPU pinning, which means when you run a container in a Docker, you can tell it that, okay, I want this container to run not everywhere, like do not resort to hardware, not hardware, the Linux kernel scheduler of threads to CPU cores, but I want this thing to run on this specific core, or this specific NUMA node, or this specific CPU package, the physical unit. And it also allows you to do other things we don't do yet, but we plan to do, like we can pin things not closer to the core, but for example, closer to the core that is connected to the PCH, so it's closer to the network adapter. So if you have multiple different workloads on the same server, like you have a number crunching app and some app that does network I/O, then you can put this app closer to the network card, and it will actually run faster. So we've put these three things together, and we've built a tool that is right here. This tool is basically a thing that will analyze your hardware topology on the local machine using the OpenMPI library called libhwlock. And based on this information, it will try to spawn multiple instances of your app, basically of your container. You can put whatever you want in this container. It can be Golang, it can be Nginx, hence the benchmarks in the third slide. And then it will spawn all the instances of these containers, and then it will put configure a load balancer in front of them so that your external client or your other app, if you use like some sort of microservice-oriented architecture, would still see it as a single instance running on the single box. So it uses GORB for load balancing, which is a tiny thing I wrote. It's based on IPVS. IPVS is a kernel built-in load balancer. It was around for like 20 years, but not many people know about it. So it's actually built in the Linux kernel. So it doesn't need to copy data anywhere. So it has very low latency and very high throughput. This is the same load balancer that is used in Docker Swarm right now. So I'm not kidding. It actually works. So it integrates with IPVS to set up a load balancing in front of your app. And sometimes I do demo here, but I don't have time for a demo. So you can check it out yourself. It's on GitHub. It's open source and free. It's written in Golang as well. And by using this thing, we've seen performance gains by up to 2x without changing a single line of our code, just by pinning stuff to CPU cores and using the terrain that is available to us, which basically means that we started to think a little bit about the actual hardware that we use to run our software, and this little glimpse of intelligent thought helped us to save half of the hardware that we have without changing any code. So, yeah, let's make programs computer friendly again. Questions? Can't really see.
Quick question. I know that the Java VM supports NumaWare garbage collection. Do you know, for the Golang VM, are they just not doing it right now, or they have no plan of making a NumaWare?
I'm sorry, it was a little bit quiet. So you said that Java VM supports NumaWare allocation?
Garbage collection. So the VM itself knows about Numa.
Yeah.
So the Go VM doesn't seem like it's doing it right now. Are they planning on doing it, or they have no plans to do it?
So you're right that Java VM is probably the only VM right now that actually understands hardware. It has a built-in support for NUMA awareness, so it will actually know that this memory is located on this NUMA node, so we don't need to migrate it, and if we do some sort of like fibers or whatever, then we understand what's going on in the memory, and it will make it efficient. Go Runtime doesn't have this support yet. I don't know when it will have it. There is it's not even a white paper, there is like this Google doc that explains how it's supposed to work, but it's not there yet. So my theory, and it was sort of proved by a few Google engineers I've talked to, is that the way Google runs this is that they run many small instances of things, because they use Borg, which is like a scheduler. It allocates things in slices, so you will run many small instances of your apps, right? So they just don't really need to solve this problem right now. I mean, they need it because of the community pressure and other big companies starting to adopt Go and the wide scale in production. But like if you're a small startup, you just don't see this. It doesn't happen. Like this issue is not an issue for you yet, right? If you're a large company, then maybe you don't use Go that much yet. Maybe you use C++ or Java, as you said, for example. And Google themselves, they don't see this issue because they run these small instances instead. So basically, our idea was like, let's do the same thing. Let's start many small instances instead, and don't start like a big, huge Go process that occupies all the resources on the server. So yeah, answering your question, Go Runtime doesn't do any hardware awareness yet. I think that's all, right? Okay, thank you again.